Okay, so I hope that all of you come back. So let's talk about the transfer sensitivity. What does it mean, transfer sensitivity? We are going to have a strain measurement. That is, we would like to have a local measurement. Strain is a local quantity, okay? So what we need to have is that you must have this cable, this resistive cable, the smaller the possible, because we would like to have the information at a point in your whatever structure, okay? That is why we are required to shrink, to have the length of the cable, everything in a very contained, in a very small area, okay? In order to do that, and trying to keep the length of the cable the maximum possible, what we need to have is that the cable should be made of some of different turns like this, okay? This configuration is much better than this configuration if L is the same. Okay, why is much better? Because we are shrinking everything in a very small portion of the measurement point. Okay, but because of that, and if this is, for example, the longitudinal direction, okay, so if we be precise, then we should be a cable of this. Okay, L and L. So if you are using, and generally that is what is done, this kind of configuration, the best one that is measuring a very small portion of your available surface, for example, then we have to take into account this portion of the cable, okay, okay, introduce additional strain because of transverse measuring direction. Okay, and this transverse measuring direction change of the length is due to the transverse sensitivity or the transverse behavior of your whatever material. Okay, so in order to take into account this effect, we have to rewrite the general strain gauge measurement, the one that is written here. Where is it? Yes, this one. Now should appear the screen. Okay.
Sorry, Professor, would you please explain briefly again transverse sensitivity?
Yes. By referring to the general equation for the strain gauge measuring, that should appear here in the classroom in a few seconds, hopefully. We are assuming that we are having a long cable, okay? But by having a long cable, we are not taking a good measurement because strain is a local measurement. So we have to shrink everything in just one point, theoretically. So in order to keep the length of this cable, this resistive wire, the longest possible, then the general configuration is like this here. Okay, it is on the left of the screen. If the length of this cable is the same as the straight cable here on the right of the screen right now, then the change of resistance should be the same, okay? But however, the left configuration is much better because it's a local one compared to the other one. And because we are willing to measure a local quantity, the strain, the left side configuration is much better, okay? Because the same length is shrink into a very small portion of the area compared to the other one. And remember, we would like to add information local in a point because strain is a point quantity, okay? But if we are having some advantage of having such a kind of configuration, we can see here that there are some orthogonal direction. We have the cable directed in orthogonal direction compared to the measuring direction. Okay, so if your material is sensitive, is having a Poisson ratio, as all the material have, okay, materials have, then you are having a change of resistance not because of the strain, but because of the strain in the orthogonal direction. Okay, and that is what is called the sensitivity to the transverse measuring direction, or the transverse sensitivity as well. Okay, how can we write that? We have to recall the basic equation that we got so far, that I'm going to rewrite here. dr over r equal to k epsilon, and then we have to add the additional contribution because of the transverse measuring direction, because of the configuration. So plus, let me call that ky epsilon y. That is the equivalent strain gauge factor and the corresponding strain in the orthogonal direction. Okay. By the way, you know very well that the Poisson ratio is the ratio between these two strains. So we can say that the ratio between the epsilon in the y direction, the orthogonal one, and the epsilon in the longitudinal natural direction is equal to negative the Poisson ratio. And because we are testing it, we are trying to find out the major effect, we can call this Poisson ratio as the Poisson ratio of the calibrating material in which we are bonding the Earth strain gauge. Okay. So the overall change of the resistance because of that could be rewritten as K epsilon negative knee calibration. Let me shorten name. Ky epsilon once again, or in other words, K1 negative knee calibration, Ky over K strain epsilon. Now it is defined the transverse KT sensitivity factor the ratio between the two strain gauge factors, so Ky over K. Okay, and then we define the strain gauge global factor, okay, as K times 1 negative mean calibration transfer sensitivity K factor. Okay. So at the very end, with that definition, okay, we can have that your dr over r is equal to kg epsilon once again. Okay. And that is very, very important because we are able to express to use the same equation, okay, just by introducing the transfer sensitivity factor into the global strain gauge factor, kg. By the way, I would like to mention the fact that the kg is a quantity very, very small, actually. So what we can say is that note that kt is so that is bounded by, let's say, 10% grain value. Okay, so kt is very, very small quantity. So we can generally confuse kg, the global strain gauge factor, kt, so that kg is practically k. Okay. Moreover, because of this configuration, the measuring configuration here, in order to reduce the sensitivity of the strain gauge, remember the main configuration is here on the left, okay, sort of grid. The wire is set in a shape that is maximizing the length, try to minimize the area which is defined. Okay, so a way of reducing the transfer sensitivity is just obtained recalling the resistance. The resistance is dependent on the cross section. So if we increase the area of the cross section part of the wire, then we can reduce the resistance and therefore we can reduce the sensitivity to the transverse strain. Okay, so what is generally done is we add additional material to the portion of the cable that is oriented into the orthogonal direction with respect to the natural one. So if I am drawing your strain gauge layout like this, for example, okay, you are seeing this as a magnified, okay, vision of that. Then we are adding additional material so that the cross-section part is reducing their contribution to the overall resistance, like this, okay? Okay, please remember, this is the natural measuring direction. Okay, that is what I call Y measuring direction. Okay, transverse. So by adding material, okay, the transverse resistance is minimized. And thus, the effect on the strain is minimized as well. Okay. So please remember that correction, the usage of kg instead of simply K. So the use of the global strain gauge factor that, remember, takes into account of the sensitivity to the transverse measuring direction, okay, is recommended when grid is short and with large section, or high, we are having a high degree of misalignment. Okay, between the measuring direction and the most important strain direction. Okay, so these are, sorry, the most important reason why to take into account kg instead of simply k. Remember, k is practically 2 in value. Kg depends on the transfer sensitivity factor, okay, what I call KT. Generally speaking, is a very small quantity, okay, but it could be of interest. It could give the differences, okay, and this is very important. Thus, when you are having strain gauge setup that is composed by grid that is short and with large section, so it is important the transverse part of the cable. And when the natural measuring direction of the strain gauge is highly misaligned with respect to the actual major strain direction. Okay.
Yeah, Professor.
Yes.
In case of transverse sensitivity, suppose if you increase the thickness, then it will affect the sensitivity. So it is prone for more errors and strain, right?
We are talking about which thickness?
The thing which we are increasing now for reducing the resistivity, which you are just talking about, the adding element to wire.
So here.
Yeah.
Okay, yes. If you think of the resistance, the orthogonal direction is introducing a resistance that is sensitive to the strain in the orthogonal direction. So you would like to minimize that. So the larger is the thickness, the higher is the area, the cross-sectional area of the cable from the resistance point of view. And then by recalling the formula that gives you the resistance, then you are having very small value of the resistance there. And therefore the contribution to the change of the resistance is limited. That's the reason why we are doing that. And therefore you are right, by increasing this thickness, so the area of the cable, you are minimizing the effect, the transfer sensitivity effect.
Okay, Professor.
Okay. If you go back to the notes, where are, okay, here, you can see that the global strain gauge factor, Kg, depends on KT and depends on the calibrating material. Remember, you have to check this when you are bonding your strain gauge to the material, to the surface of the material, test material, so the test specimen. So this Kg depends also on the material that you are using to give the information of the transfer sensitivity. And in this, indeed, these specs that are given when referring to strain gauge are also referring to the material used to calibrate your strain gauge. Okay, so please consider that the measurement will give accurate result when using the calibrating material for the test specimen. What happens if you're not using the calibrating material? So what happens if you are using your strain gauge in a different material? I mean, for example, you are calibrating, and therefore you know the information of the KT for that strain gauge when bonded to a titanium material. What happens if I'm now bonding that same strain gauge to an aluminum material, for example? What happens to the transfer sensitivity? What happens to the error? So let's see together what is the error induced by the transfer sensitivity when using a different material than the calibrating one. Okay. How can we answer to this question? We can define the error first. So the error is the percentage, the difference in percentage of these two variation of the change of the resistances, because we are using the strain gauge with the calibrated material and the actual material.
Sorry, Professor, can I ask a question?
See, yes.
So do you mean that for different materials we should have different calibration?
No, what I'm saying is that you are calibrating the strain gauge with a few number of materials. Then the question is, what if I'm using that strain gauge with other materials? So what is the effect on the transfer sensitivity because I'm using a different material with respect to the calibrating one?
So if I calibrate this device with steel and aluminum, there is no error for steel and aluminum, but for other materials, there may be some errors. Am I right?
That's correct. You know just one calibrating material. I mean, you know that that strain gauge has been calibrated using titanium. Okay. So you got good results, acceptable results, very accurate results if you are bonding that strain gauge on a titanium material. But what if you are doing that, you're bonding the strain gauges in a different material, let's say aluminum and so on. So this introduces an error. What is this error? Can we quantify that error? That is what we are going to do now. Okay. So
Thank you.
You're welcome. Now let's define the error eta as the ratio of the change of the resistance when using the actual material compared to the change of the resistance when using the calibrating material, of course, with respect to the calibrating material. Okay, this quantity is telling you what is the error. So the task now is find out a useful equation that is giving me the information on this eta, so this error. Okay. error in the transfer sensitivity because I am using a material different from the calibrating. Okay. Remember, the change of resistance actual is giving you by K epsilon, oh sorry, K epsilon plus Ky epsilon y. Okay, remember, K is the stage gate factor, epsilon is the stray in the natural direction, the longitudinal one. Y is referring to the transverse direction with respect to the longitude. The same we can say for the change of resistance with respect to the calibrating material. And that is given by K1 negative knee calibration that we know very well, KT, and then epsilon. Okay. Of course, we don't know anything about the other parameters. We know anything about the calibrating material. If we substitute now to the previous equation, what we got is that error eta is giving you K epsilon plus Ky epsilon y negative K1 negative calibration KT epsilon everything divided by K1 negative calibrating KT epsilon. Remember, KT is equal to, by definition, the ratio between Ky and K. That means that eta could be rewritten as KT epsilon y over epsilon x plus the calibrating epsilon x divided by 1 negative the calibrating epsilon x. Okay, I made some simplification in the way. So we can simplify this. And at the very end, what we got is that this error, eta, is going to be equal to the knee calibration negative actual value of the posture ratio divided by 1 negative knee calibrating KT times KT. Okay, that is the result. As you can see, if you are using this strain gauge on the same material of the calibrating one, then the error is 0. That is, if epsilon y over epsilon is equal to negative recalibration, okay, let me rewrite this. Is coincident to this one, then what does it mean? It means that your eta is 0. Okay, as expected. Go up and you can see that. Yeah. Yeah, if the calibrated material is equal to the actual material, numerator is 0, and that error eta is 0. Okay. Now I'll give you an idea of what are these values. So if, on the contrary, we are having a different material, for example, if you are considering an aluminium, so if the calibrating is aluminum. Then what we got is that KT is practically, could be practically 0.005, that is 0.5%, so very, very small. Oops. Okay. And for that, the Poisson ratio is about 0.33. Okay. Now, once we made this effort, we have the information of KT of this strain gauge material system composed by the actual strain gauge and the aluminum. Now, if we are using, so if the strain gauge SG is used, on a testing material that is titanium carbonate, that is having your Poisson ratio equal to 0.18. Okay, then you can easily find out that the error is 0.0226 kg, that is of about 0.011%. Okay, so as you can see, we are having a very small contribution, okay, to the actual identification of the strain because of the transfer sensitivity. Okay, we have to consider that, of course. I just want to end the class with the some configurations. Okay, some discussion of the configuration. So, strain gauges are found out at the store in a wire configuration, okay, as I told you before, okay, in a, say, modern version of that, but also photo engraved. On a host structure, okay. This new configuration, the photo engraved one on the host structure, allows different measuring configurations. Minimum size of the measuring grid, about 0.05 square millimeters, so very tiny. Okay, and they offer larger radiant surface that is very useful for heat dissipation. As we can see later on, this measurement, the strain gauge measurement, requires the connection of this strain gauge to a measuring circuit. We will see later in a few days what happened, okay? But before enter to details, let's assume that because we are having this measuring circuit, we need to dissipate the heat that could be generated because of the Joule effect into this measuring device. Okay. Generally speaking, they are robust. We can use them many times, and we can have that the cost is very limited. So just to give you an idea, a pack of about 10 strain gauges costs about, let's say, 150 euros to me, okay? Maybe double for you, but that's okay. Okay, having said that, I just want to make this calculation and then I close the class. Let's assume to have the resistance. The base resistance typically is 120 ohms. Let's assume that we'd like to measure a strain of about 100 microstrain, okay? Typically. Let's assume that our strain gauge is characterized by strain gauge factor of 2 equal to 2. The question is, what is the expected change of resistance in such a configuration? Remember, the change of resistance, sorry. Okay. The change of resistance with respect to reference resistance is given you by K epsilon. Now, if you plug numbers, what you just found out is that the change of resistance is 2 10 to minus 4. That is, the change of resistance is of about 2.4 10 times 10 to negative 2 ohms. Okay. What do you think about? Do you like this? How do you like this result? They are very small.
Mm-hmm.
Have you ever played when you were young with the multimeter? I mean, the measuring device that is capable to measure the tension, the current, and also the resistance, the one that you hold between your hands and see what is typically the resistance of your body. Okay. Well, if you go back to those times, you will easily remember that the minimum quantity that could be measured by such a kind of measuring device is, let's say, a ohm. So we need something special in order to use such a transducer. Otherwise, they are useless. The noise and uncertainty is very high. Okay. Okay. So I'm stop here. So I'm giving you back the 10 minutes that I owe you, so that now we are we are okay, we are balanced. Do you have any question?
Professore, mi scusi,
Prego.
puoi ripetere quest'ultima cosa, per favore?
Sì.
Grazie.
So if you refer to the typical values in the strain gauge measurements, that is, we are having a base resistance of 120 ohms typically. We would like to measure a strain of about 100 microstrain, and you are using a strain gauge with a strain gauge factor K equal to 2. What you found out is that the relative change of resistance is about 2 times 10 to negative 4, or the variation, the resistance is 2 something, 10 to negative 2 ohms. That is, we are having, in the typical working condition, a change of resistance that is very tiny. Okay. If you experience the measurement of the resistance using the multimeter, the one that probably you used when you were young, you easily recall that the minimum value of the resistance is, let's say, 0.1 ohm. Here we need 0.01 ohm, even less, okay? So what you need is a special measuring device that is capable to be accurate enough with such a very tiny value of the change of resistance, okay?
Ok, quindi è solamente un problema di strumenti, quindi servirebbe uno strumento molto più preciso, cioè più...
Correct.
Ok,
Yes.
grazie.
Yes. And such a kind of measuring device are called bridge measuring device. We will see that how we can use it.